These maths teachers are taking part in a project that's looking at the ways ICT can help with hard-to-teach secondary maths topics. Leading the project is Alison Clark-Wilson of the Mathematics Association and her colleague, Professor Adrian Oldknow.
Everything else changes on the screen.
The group has come together to share resources they've developed and used with their own pupils. What each topic has in common is the use of ICT to tackle a traditionally tricky topic.
I've been looking for some time at circle theorems and using ICT to support that.
Ruth's Circle Theorem project uses dynamic geometry software, which allows pupils to make and manipulate their own geometrical constructions.
This is the one we liked, didn't we? You know, they've done quite a lot there, and I'm particularly interested with these students to look at geometric reasoning and also proof.
Before she tried this topic with her pupils, Ruth explained her plans to project leader Alison Clark-Wilson. One group of pupils would have step-by-step instructions for what to construct and what to investigate. The second group would have a set of cards with fewer instructions.
So this one, when they come, it just says construct a circle, construct a triangle whose vertices all lie on the circumference. Yes. Make some conjectures about the angles you've created.
And the third group would have just the text of the theorems themselves to work from.
This is going to be a real experiment. Let's see what happens with these students. So, number one says, show that the angle subtended at the centre of a circle is twice the angle subtended at the circumference.
Yes.
So their focus is very much on proof.
Yeah.
Ruth hands out the prompt sheets and cards for her Year 9 pupils to get started.
From the File menu, choose New Sketch. Construct a circle. From the Construct menu, choose Line.
They've used this software a few times before and have done some work on the properties of triangles.
Now you've got to construct an isosceles triangle with the odd angle at the centre.
The odd angle of the centre?
Yeah, you know how to do that.
Right.
Click that one.
Where did you start?
The students have set up the software to display the angles in their triangles on the screen, and it's not long before they come up with some conjectures.
Every time we move the C angle, the B, the other angles all change.
When you move the points around the circumference, all the angles change in the triangle when it's in a circle. Apart from...
What's the one that stays the same?
That one.
Only two change at a time. So you can write that down.
It was asking about, like, if you made a triangle, what the angles would be if you moved points around the circumference. As we did there, we found out that B would always stay the same and A and C always change. But A and C, when you add them up, they'd add up to 90 degrees. And B would always be a 90 degrees.
The angle of C on this side of the chord
is 45.52 degrees.
Right,
all the way around.
Yeah.
But when it goes below the chord,
Yeah.
it changes to 134.48, which both the angles add up together to create 180 degrees.
Fantastic.
The pupils working on the orange cards begin to devise some actual proofs.
Yeah, we cut it in half, so there's two isosceles triangles.
Ah, right, interesting.
Because we've been learning about isosceles triangles.
So isosceles triangles are pretty important.
Yeah.
Ah.
And the measure angle.
I know you want to measure some angles. Okay, I'm going to leave you to that one. I'm going to come back to you and see how you get on.
Measure. 46.
Should that be equal to that?
Yeah.
We'll just make sure.
I cut it into two to make two isosceles triangles on both sides.
Good.
And that means that the two opposite angles should be the same size.
Good.
And there should be one odd angle.
Good.
So I worked out the middle angle.
Yes.
And from that I got the other two angles. So I divided that by 2 to get the other two angles.
Right.
The angle in CEDH, we were trying to prove that that is twice as big as the angle in here, CFH. And what we did was we clicked on the 2 points, F and D, and drew a line through. So we have both angles.
So they're isosceles triangles.
So we created two isosceles triangles. So
these two angles added together, the two similar angles, must equal
Exterior.
the exterior angle here. So this is exactly the same isosceles triangle. It's another isosceles triangle because it's got two radii. So we've got two of the equal angles from each triangle. So this must be two. It must be double what they add together to equal that.
And it's asked us to make some points going to the middle from angle A and C.
And to measure.
And to measure them.
And then it's asked us what do we notice. And we notice when we move like the angle B, it's at 70, say here, it's at 72.85 degrees.
How would they have tackled this project without the geometry software?
Normally, you can't really move angles on a piece of paper, really. It won't really do much, will it? So a computer using this software is really good because it lets us experiment. While it's not that hard, but you can learn so much out of it.
First you set up the circle, then you put 2 points on the circumference of the circle, construct a line, select midpoint on the chord, then you select the midpoint and the chord and construct a perpendicular line that sends a line going through the centre of the circle. Wherever you move the points on the circle, the perpendicular line will always cross through the centre of the circle, and there'll always be a right angle on the point and the chord.
Clearly, the students found the software very useful for this project, just as their maths teacher had hoped.
Do you think that using the software enabled them to do more maths or enabled them to go further with circle theorem than you might otherwise in Year 9, Ruth?
Oh, definitely, yes, I think so. And I think it allowed them to go further in the sense they got freedom and they weren't sitting working through a textbook getting stuck,
yes.
Which is what you might expect if they had this sort of thing.
Yes.
They were able to try things out and in a reasonable amount of privacy, actually, in the sense that, you know, they weren't sitting in front of the whole class doing things. And I think definitely they've got... I mean, I wouldn't normally perhaps even start on circle theorems in Year 9.
Yes.
But I just thought it'd been interesting to try with them and see what they could do.
Yeah.
And I think they've certainly gone beyond an average Year 9 at this stage.
I decided to go away and look at one of the things I thought was hardest to teach, which was solving 3D geometry problems.
Ashling's hard-to-teach project involves using 3D geometry software to help her pupils visualise and understand the properties of three-dimensional shapes.
There were the side length they had.
Before she used the materials with her pupils for the first time, Aisling showed Professor Oldknow what she was planning to do. He's an acknowledged expert in how to use this software.
One of the most important features of Cabri is the fact that we can actually open up a shape.
Is that something they've tried before, or will it be something quite new when you do that?
Some of the students should have done this before when studying nets.
Right, OK.
So we're looking at the fact that this is a right-angle triangle.
What is so hard for pupils about working in 3 dimensions?
The hard-to-teach element is the fact that we're no longer dealing with a rectangle or just any old 2D shape. And when you're presented with something like this, people find it very difficult to visualise breaking down the object and opening up the object in their heads. And I think when they see it on something like Cabri, it just changes their thinking process a little bit.
It's so hard to teach, it's usually not done. It's usually cut out. I mean, the amount of 3D work that's actually done in the secondary school compared to the preparatory work that's done in primary school is pretty tiny. It's usually omitted because it's actually also very difficult to test. On the other hand, we all function in a 3D world.
The whole idea throughout this lesson is that students will connect, that you can use this to help you while still being able to solve the problem by yourself with a pen and a calculator if you have to. And I suppose you have to keep that in mind, and that's what teachers would often be worried about, I think, because they think that when you start using something like this, you throw away other methods and other uses, but that's not, it should complement that work. And the problem I have for you has got to do with a box.
In the lesson with her Year 9 group, Aisling introduces a 3D problem.
Okay, this is Joey's box. And Joey is having a bet with his friend Jasmine. And the bet is about what is the longest stick that would fit into this box. So what I want you to do for a moment, I'm going to pass some boxes around, is have a little chat with the people around you and try and figure out what you think the right answer might be for a box like this.
So how long do you think that this is, like the length of the rectangle is?
So like we could put a line through it, work out the length of this one, then we know like how long the stick can go in there. We can use Pythagoras.
Measuring it that way is going to have a longer stick than measuring forward like that. So we're going to measure it that way to see how long the stick can be.
They then look at an interactive version of the same box made on the software.
Thank you very much, Vivian. Okay, so Vivian has actually opened up the box so that we can see inside of it. This line, which is one of the sides of our cuboid, is 8.2 centimetres, whereas the diagonal is actually 9.9. Right, is that the longest stick that could fit in, do you think, into this box, that 9.9 centimetres? Do you have another idea for me?
You can measure from E to C.
From E to C, right. So then you're actually finding the diagonal from the top vertex to the bottom vertex of the cuboid. So if we measure the length of that segment, 11.5. Well done. I'm going to rotate the shape so we can have a look at it from different angles.
Is it triangle?
Does anybody have anything they want to mention? Denai?
Yeah, you can see a triangle inside of it. I think it's from points E, G and C there.
So you want me to go from point E to G to C. Okay, let's rotate that and have a look at it. So if we don't know this length here, how can we work out what it is? Elise?
To find the length, you could use Pythagoras theorem.
So we know that, for example, this side is 5.5 and this side is 8.2, so we can work out what EG is. Once we know EG, we already know that from G to C is 6, so we can use our value from EG and GC to find the length of the longest diagonal. So in fact, in this problem, we have to use Pythagoras twice. Okay? I want you to try that out with the person beside you now, please.
Although the software can give all the measurements automatically, Aisling believes it's important for pupils to back up what the software can do with the written methods they're expected to use in the exam.
We're trying to work out the pink triangle at the top first. Find the hypotenuse. So it's 5.5 and 8.2.
Yeah, 5.5, 8.2, and the hypotenuse
equals C squared. 8.2 squared is 67.42.
What I want you to do now is on your laptops there's a folder called 3D Geometry.
The next task asks pupils to use the 3D software to work out the angle between the diagonal of the cuboid and its base.
So you're using open polyhedron, and now you can pull down the net. So what should you do first, do you think?
Find a segment. Do a segment.
Super. So go to the segment 2 for me. From A. Yeah.
To
Super.
We have to draw a triangle to find out the angle in between here, here and there.
We're going to measure the angle here, right? Yeah, the angle there. So.
How would you check that it's actually 49? Trigonometry. So you could use the opposite and the adjacent length here to find out the angle.
Here, the ICT provides a stimulus for mathematical discussions.
So it's supposed to find length from A, B, and C. That's going to be a triangle. That's a right angle triangle right there.
So now we've got all our lengths in our triangle. How will we work out the angle?
I think you should just go on the angle one and then just measure the angle.
Okay, super. Off you go. How would you check that this was the right angle?
Do like a
another line there.
Yeah. Segment.
Some pupils move on to work out the longest pencil that would fit into a square-based pyramid.
Oh, first we have to open it. How about this one? How about
Do we think that's going to be longer than maybe something coming down from the top?
Let me try. We predicted that the longer side is going to be from there, from one corner to the middle of the pyramid, which came up to 7.6. Now, what we need to do is just find the angle of it. So we're going to work it out using Pythagoras' theorem and then check if it's right.
Other pupils had true or false statements to investigate. For this, they would have to construct the 3D shapes for themselves.
It just means that we're trying to figure out if these statements are always true, or if they're sometimes true, or if they're never true. So you can use any of the documents we've used today, or you can construct a new shape yourself and try and investigate. You can start wherever you want.
The larger the volume of the cuboid, the larger the angle between the diagonal and the base. So we're just trying to make the cuboid now and trying to find out the angle.
So you make a diagonal between, let's use H and B, or E and C, whatever. The larger the volume of the cuboid, the larger the angle between the diagonal and the base.
So there's your volume. What else do you need?
And then extend.
You can actually make it empty. So now you can see through the shape and you can see your diagonal clearly here. The girls that are on the open-ended tasks that are working on the extension questions are doing really well with the investigating aspect. So they're using Cabri to kind of figure out if their ideas are right or wrong. The thing is, like that, when they can make the cuboid bigger and smaller at the touch of a button, it's something they could never work out with a pen and paper. They cannot see, you'd have to continually measure the volume, find the angle, make it bigger, measure the volume, find it would take forever. So I suppose they've come to a realisation really quickly.
As you make the volume even tinier, the angle increases. When you enlarge the cuboid, the angle begins to decrease. So this makes the statement false.
So how did the lesson go?
I think it went quite well. The students did really well with the software. I think they learned a lot about using geometry in 3D space. And I think the kind of approach that people normally take to that topic, students often going away feeling more confused than when they walked in. And I think these girls feel like they could tackle a problem like that, which is a real achievement.
I mean, what struck me particularly is that in the end, they're doing the same kind of maths in their books that they'd do if they just saw a static picture on exam paper.
Yes.
But they've seen something they can manipulate and move, so they've got an added experience.
No, absolutely. I think the whole thing about this is when students first meet any kind of maths, if they get a kind of an impression that this is confusing or this is difficult or I can't picture this, it tends to stay with them. And the girls today were able to take apart the shapes and manipulate things, and they really got the feel for what this is about. And although you mentioned they're using the same maths they would in essence use if they were looking at a 2D picture of this problem, they now understand why they're using that.
And I was thinking really about algebra and sequences, and thinking about how I can link together the many representations of sequences.
Jay's project involves using this handheld computer device to investigate quadratic functions and number sequences.
This function is x squared.
What made you pick this particular topic?
Before he tackled the topic with his pupils, Jay and Alison discussed what usually makes it so difficult.
Quite often it's taught in different parts, and although students learn the square numbers sort of lower down in the school, they often don't look at the representation of quadratic functions until a couple of years later. And if it's being done by pencil and paper, by the time the students actually drawn all these out several times, they might have lost a sense of what this was all about. Whereas what we're doing today, they'll see the quadratic function plotted instantly on the ICT, and they'll be able to make those connections a lot quicker.
Jay then downloads the files the pupils will need from his laptop onto each of their handheld devices.
The number sequence we're going to look at first starts with the number 1. And the next number is the number 4. And the next number is the number 9. And then I've got the number 16.
Jay starts the lesson by setting out a sequence of square numbers and the corresponding patterns of squares. He then prepares to enter this sequence of square numbers into the computer software.
How many squares were there in the first one? Yes, Connor.
1.
In the second one, there were...
4.
4. Thank you very much.
9.
There were 9. Very good, very good. And in the fourth one, there were, going over to Matthew...
16.
16, thank you very much. So, that one represents 1, that represents 4, that represents 9, that represents 16. I'd like you to type them into yours as well and make sure that they're appearing on yours. That's fantastic. And you can put the fifth one in as well if you want to.
Jay's Year 8 pupils have used these handheld devices before to look at straight line graphs, but this is the first time they've encountered quadratic functions. Now, they're trying to find the graph of an equation that fits the points they've plotted.
You could put a square key and then you could put a number in there. 1, enter.
I pressed X, then I pressed the X squared button, then I pressed enter, and it just curved line.
And let's think about this for a minute. If those are your X numbers, X squared becomes your Y numbers, and then you get a graph like that. Okay.
Jay then hands out some other quadratic number sequences.
And you're trying to find what equation will go through the points that you'll get when you plot these values.
0, 3, 8, 15.
In your pair, choose one of the sequences, you can type them in, and
What should we do?
to see with the equation. So how could we get the equation from 1?
0, 0.
You're right about
3,
that. Good points. Maybe later
8,
on.
15,
Sorry?
24.
So you're right about what you're saying.
Enter.
We thought at the start we'd done the same as the last you know, I can't remember.
Last sequence,
Yeah.
which was x squared.
Yeah.
The equation was x equals.
But then but when we put x squared and we press enter, it's a bit off. So we thought, what could we do?
But
So
then we realised that every single number down here is 1 less than the squared number in the last one. So we thought if we put -1 at the end, it might give us the answer.
-1 here,
Sure.
and then press enter. It's on the line. And we got it. Yeah.
What have you noticed?
That it's just like add 10 in it.
Oh, it's add 10. So what was the equation we used last time?
X squared.
X squared. And this is, you just said it was...
Add 10.
So what do you think you might try?
X squared at 10.
Try it.
Yeah.
No. This could be right. Oh, wow. Well done.
So we do 0, 3, 8, 15, and then we do 24. And then you press Control and Tab to go onto this bar. And then that's the equation sign. So the equation would be x squared minus 1. Yeah, that's it. X squared minus 1.
What I'd like you to do now is just to pick one of the sequences you explored. I'd like you to draw for me the number pattern that goes with it. I'd like you to write down what the numbers are. I'd like you to sketch the graph that you got and write down the equation that you use. So all these 4 things here, 1, 2, 3, 4 things, I'd like you to write them down. They all represent the same thing.
1, 2, 8, 9. There's 1, 2, 3, 4, 5, 6, 7.
You done 1.
Okay, now, what have you found out today?
I found out that, graphs, I thought it'd just be
Yes.
9 bar graphs, like pictograms and telegrams. But
Right.
this one is different because you're using square numbers. I didn't know that you could transfer like square numbers onto a graph.
Okay, and what was special about the graphs that you got?
It's curved.
most all of them are like lines and stuff, but this one's curved.
That was something new for you. Fantastic. Did anybody notice anything interesting about how the graphs varied? So if you had x squared minus 1 or plus 5 or plus 10?
Okay, if you did x squared, it would be low, but if you did plus 5, it lifts up and goes higher.
How high would it go then?
5 times more higher.
It would go 5, OK. And if you did x squared plus 20, what would happen then?
It would go, like, lift up to 20, go through 20.
And if you had x squared minus 1?
It would be minus 1.
Minus 1. Should we just have a look at that on the screen? Because I'm not sure everybody spotted that earlier. What will happen if that was x squared plus 1 instead of x squared plus 10?
Where the curve is, it'll go lower.
It would go lower. And what number would it go through on the y-axis?
It'll go through 1.
It would go through 1. Let's have a look. So going over to my computer again and changing that. Change it to a 1. Oh, look, and you can just see that is 1, because there's 0, there's 5, and that's 1. OK, I think you've worked really well today, so we'll stop there. Thank you very much.
So what was Jay's reaction to the lesson and his pupils' work?
So much happened, really. What struck me as significant is that this was their first introduction to quadratic graphs, and they hadn't seen them before, and the fact that they were curved really came alive for them. They'd not seen curved graphs before, so that was quite fascinating. And had I done this on paper, it would have taken quite a long time to get those connections that we saw today, which is nice because the focus wasn't on the ICT, the focus on the maths. And so often people think of maths with ICT as actually being an ICT lesson when it isn't at all. It is a maths lesson. And when we asked them at the end what they'd learned, it was all about quadratic sequences. It was all about the shape of the graph. It's all about the fact that you can plot these things. It was all about the mathematics. And not about the technology, but technology was necessary for that maths to take place.